for joining us. I'm Faith Ellen. I'm a professor of computer science at the University of Toronto, and I'm one of the long-term visitors to the fall 2018 program on lower bounds in computational complexity at the Simons Institute. For those of you who are here for the first time or watching on video, the Simons Institute is the world's leading venue for collaborative research in theoretical computer science. Established in 2012 with a grant from the Simons Foundation, the Institute brings together the world's leading researchers in theoretical computer science and related fields, as well as the next generation of outstanding young scholars to explore deep unsolved problems about the nature and limits of computation. Today I have the pleasure of introducing Anil Ananthaswamy, who is the current journalist in residence at the Simons Institute. The Journalist in Residence program was created in fall 2016 with the goal of increasing visibility for theoretical computer science and supporting science journalists interested in covering the field. Resident journalists participate in the Institute's programs and engage with visiting scientists. They also give talks on their work and offer advice to scientists who would like to learn to communicate their work to the public. Anil Ananthaswamy is an award-winning journalist. His first book, The Edge of Physics, which he'll talk about today, was voted Book of the Year in 2010 by Physics World. His second book, The Man Who Wasn't There, won a Nautilus Book Award in 2015. In September, he talked about his recently published third book, Through Two Doors at Once. Anil is a former staff writer and deputy news editor for New Scientist magazine. He's a freelance feature editor for the Proceedings of the National Academy of Sciences, Front Matter. He's also written for Nature, Quanta, Nautilus, and Discover magazines. Anil has been a guest editor for the science writing program at the University of California, Santa Cruz, and organizes and teaches an annual science journalism workshop at the National Center for Biological Sciences in Bangalore, India. Before becoming a journalist, Anil worked as a software engineer here in Berkeley. When I was asked to introduce this talk in early November, I decided I should read The Edge of Physics. I found it a fascinating combination of travelogue and history of mostly recent science. Specifically, it describes the huge experiments that particle physicists and cosmologists have been doing to detect neutrinos and dark matter, and the mostly remote locations where these experiments were being performed, including Siberia, the Chilean Andes, Mauna Kea in Hawaii, the Kuru Desert in South Africa, Antarctica, and the Himalayas. I really enjoyed the interesting details he mentioned, such as the statue of Shiva outside the particle accelerator at CERN Geneva. Shiva's dancing inside a ring of fire, scattering the darkness of illusion. I also liked the stories he told about the people involved in science. For example, when Joseph Taylor won the Nobel Prize in 1993, he invited Jocelyn Bell to join him as his guest. This was Taylor's way of acknowledging her discovery of pulsars, for which her advisor won the Nobel Prize in 1974. Today we'll have a chance to hear from Anil about his experience writing The Edge of Physics, the challenge of combining travel and science, and the reasons why he chose this format for the book. Please join me in welcoming Anil Ananthaswamy.
Thank you, Faith, for that introduction, and I'm really honored that you actually read the book. I must admit, it's been a long time since I researched and wrote the book, so I had to read the book to figure out a few things that I had forgotten myself. So, let me, is this working? Great. So, what I want to talk about today is a little bit about the travels that I did for writing The Edge of Physics. These were, as Faith mentioned, travels that took me to some very remote parts of our planet, Siberia, the Atacama Desert in Chile, all the way to the South Pole. So, and there was a reason why I wanted to write a book which was focused on these locations, and the main reason was really to bring about a feeling for physics. As much as I was going to describe the science and the experiments, I also wanted people to feel a certain way about what's being done, and I felt like describing these remote locations was going to be a way in to to accomplish that task. The research for the book actually began here in Berkeley. I had just become physics news editor back in London when I was working for New Scientist, and I was visiting Berkeley, and I met Saul Perlmutter. That name may be familiar to you now because in 2011 he won the Nobel Prize for having discovered that the expansion of the universe is accelerating. He's a Lawrence Berkeley National Labs and researcher, and I think he might also be faculty here, I forget. But in 2004, when I met him, we met at a Starbucks at the corner of Cedar and Shattuck, for those of you who know. It's gone now, the Starbucks. And he hadn't yet won the Nobel Prize, so I could actually get to meet him in a Starbucks, which won't be possible now. And I was trying to tell him about this idea I had where I wanted to visit mountaintops and write about telescopes and also try to tell a bigger story about the physics. And it was he who planted this idea in my head that you don't have to restrict yourself to mountaintops, that there are other things happening in physics which are very extreme, or rather physics being done in very extreme locations. The experiments are also extreme. And that got me thinking about where else can I go? And it became a fascinating sort of task to pick pretty much the most extreme locations I could find and then try and piece it together to see if there was a story, larger story about cosmology that could be told, about what's happening in cosmology, about what's happening in astroparticle physics and particle physics. So it was a combination of wanting to pick really the most extreme places possible and the most extreme experiments possible, and also trying to find a way to assemble the jigsaw puzzle of telling a larger story. And as part of that, even before I could convince a publisher to take a punt on this, I had to do these travels because the science and the physics that I was going to describe was not new. So it was not like some groundbreaking physics that I was about to tell stories about in the book. So this book would have only worked if I could write in the way that I was claiming I was going to write it. So I actually had to do a few journeys well before I had any guarantee from a publisher that it was going to be published. So the first place that I went to is a place in the Atacama Desert. It's in the Chilean Andes. This was to a place called Mount Paranal to see something called the Very Large Telescope. Astronomers have some wonderful ways of naming their telescopes. This is a telescope built by the European Southern Observatory, ESO. Their new telescope, which they're working on now, is called the Extremely Large Telescope. And believe it or not, they have another one in the works, which may or may not happen. It's got an acronym, a nice acronym called OWL, for Overwhelmingly Large Telescope. So this one, this is the first place I went to see. Let me see. Yeah, you see these domes up there. Those are 4 domes that which house 4 8-meter class telescopes, and together they make up what's called the Very Large Telescope. And the reason for going here was to both write about the construction of these amazing telescopes, but also to give readers an understanding of why telescopes are built in places like this. So this is, one of the driest places on Earth. It's on the leeward side of the Andes. That mountain is at about 9,000 feet. The air is extremely dry, and dry air is really good for astronomy. Astronomers have a term that they call seeing. So a place with good seeing is essentially very, very good for astronomy because the light that's coming in from the cosmos doesn't get messed up by the atmosphere. And water vapor in the atmosphere is a big no-no for astronomers. So this, because of its dry atmosphere, some places here have not seen rain for decades. And it's so dry that NASA tests its Mars rovers here before sending it to Mars. If it can find life here, it would find it on Mars. That's the idea. The other reason why the Chilean Andes are such a great place is because of a climatic condition. There's a cold current that flows along the coast of Chile, and this cold current causes a inversion layer. It basically pulls down the cloud cover to about 7,000 feet. So normally clouds that would be at 30,000, 40,000 feet are all pulled down to about 7,000 feet around these mountains. So these mountain tops, for most of the year, are above the cloud cover. So when they're looking up, they're getting about 350 days of clear skies. Right? So it's an extraordinary place for astronomy, and the place is literally littered with telescopes. Optical astronomy, radio astronomy, and just to give you a flavor for what they were building in the late 1990s and early 2000s, these telescopes have 4, like I said, 8-meter class. There are 4 8-meter class telescopes. So each telescope has a mirror that is 8.2 meters wide. These were at the time, and probably still are, the single largest pieces of glass that have been used for making a telescope mirror. So it starts with a blank, which is about 45 tons of glass that has been poured, and a blank is created. That's then ground down, and even after grinding it down to the required shape, it's about 23 tons each mirror, and that mirror is then being held up by a steel truss that itself is about 10 tons. And the mirrors are, because they're, I think they're about, I forget, 18 inches thick, which is actually quite thin when you think of the expanse. And so as the telescope is tracking some celestial object, it's actually deforming. And in order to keep the shape precise, the mirror is resting on 150 actuators that are constantly pushing and pulling to maintain the curvature. So in essence, the mirror is actually not anchored, it's just resting on these things. And this is a seismically active region. There are some major fault lines there, and they have earthquakes all the time. So how do you build something where this massive piece of glass is just resting on pistons in a land where you can have massive earthquakes? So the truss structure that is surrounding these pieces of glass have clamps. So the moment there is any intimation of a tremor, these clamps reach out, hold on to the mirror, and pull it off the actuators, and literally hold on to it. And then the whole mirror is now anchored to the larger structure, and the larger structure is built to sway with earthquakes. So, and earthquakes have happened. All the 4 mirrors have been protected this way. They literally lift 23 tons off the base and hold it while the earthquake is going on, and then put it back and start observing. So it's amazing. So the reason I went here was to see how these telescopes were built, to tell readers about the construction of it, what it takes to work in these amazing places, extremely dry, pretty hostile environment, and also to learn about how these telescopes were used for the discovery that I told you about, that Perlmutter had worked on and other teams had worked on, which was to find out that the expansion of the universe has been recently accelerating, recently meaning in the last 4 or 5 billion years. All notions of time and space change when we are talking of the cosmos. Recent, 4 or 5 billion years is recent. So after I finished with Chile, I came back. This would have been, I think, October 2005. I wrote it up, and then I went to see another experiment even before I had a proposal ready for the book. So this was all sort of research to put together a proposal. And I wanted to see another telescope in Siberia called the Lake Baikal Neutrino Telescope. Neutrinos are subatomic particles, which were predicted in the 1930s and were discovered two decades later. So these are not mysterious in any sense of the word. They do exist, but they're extremely hard to detect because, as the name implies, neutrinos are neutral. They can go through normal matter without interacting at all. So you essentially need very, very large detector volumes in order to find these. And one way of doing it is to look for neutrinos hitting water molecules. When neutrinos hit water molecules, they emit something called a Cherenkov cone of light, or Cherenkov radiation, which is essentially a muon that is generated when a neutrino hits a water molecule. The muon moves faster than the speed of light in water, not faster than the speed of light in vacuum, but faster than the speed of light in water, creating a wake. So it's essentially like you would have a sonic boom, something equivalent to that with light. And it's this Cherenkov radiation that, if you can detect, that's a signature. There are other ways in which this radiation can be created, but there are ways in which you can figure out that this has been created because a neutrino smashed into a water molecule. But again, it's very, very hard to detect these neutrinos. So the grand idea that the Russians had was to instrument a large volume of the water of Lake Baikal. Now this lake, so when I contacted the Russians, actually I had a German researcher who was the go-between. I was told that yes, you can come and visit us, but you have to come in March and April. March and April, if you don't know, is peak Siberian winter. And so I was really surprised. Why are they working during the peak Siberian winter? It turns out it's actually fantastic Russian ingenuity, because in order for you to build a telescope, in this case the telescope is literally detectors that are submerged in the water, which are looking for these flashes of blue light that happen when neutrinos hit the water molecules. if you had to do this in, say, seas and oceans, which have been done, you need ships and submersibles and all sorts of diving equipment, and it's very, very expensive. The Russians decided, let's just wait for the lake to completely freeze over, and then we just come every 2 months during the peak of winter and set up our ice camp on top of the lake. They cut holes in the ice, send their divers into the freezing waters to locate the instrument, which they have left behind the previous year, bring it back up, and then repair it. And they literally have 2 months before the ice starts melting and cracking, and they have to get out. So I had to go there in the peak of winter. This was an incredible experience for a writer. And so that's Lake Baikal seen from the shore, one shore. The lake is about 630 kilometers long, and it's 80 kilometers wide at its widest. It's about 1.7 kilometers deep on average. And it has 20% of the world's unfrozen freshwater. And 20% of the world's unfrozen water. It's a massive lake, right? And this thing freezes over completely. The ice that you're looking at here is 1 meter thick during the winter. So that's how cold it is. And those black dots that you see, that's about 4 kilometers away from the shore. And when I got to the ice camp, that's where the researchers were working. They were basically, this is the scene that greeted me. Now, they're basically, what they're doing is getting the instrument that they have submerged inside the lake. What they have done is they have submerged 228 photomultiplier tubes arranged in strings. These photomultiplier tubes are essentially looking for these flashes of light when neutrinos hit water molecules and convert them to electrical signals and then send them to the shore station. But that's about 1 kilometer inside the lake when they come in every winter. So they have to cut a hole in the ice, send divers in, find out where the instrument is, and drag it up. So what they've dragged up here is just buoys. The actual instrument is still inside. Every time I give this talk, I look at that man and wonder, these are all postdocs and PhDs, by the way. He was working so hard, he was sweating in sub-zero temperatures. So this was the second trip, and to write about neutrino physics and how neutrinos can also be incredible cosmological signals. So they haven't found it yet, but one of the things that they're looking for is neutrinos from the annihilation of dark matter particles. So dark matter particles can self-annihilate, and one of the byproducts of that annihilation can be neutrinos. And if you find these signals coming from, say, the center of the Milky Way or the center of the sun, where the gravitational forces are such that dark matter, which is a hypothesized particle, is accumulating in large numbers, then it can self-annihilate and you can end up with a neutrino signal from these regions. So one of the things that they were looking for is that, and also neutrinos coming from the atmosphere. When cosmic rays hit the upper atmosphere, that generates neutrinos. You can look for neutrinos from outer space, from astrophysical events. So this experiment was the first experiment which had instrumented a natural body of water and seen atmospheric neutrinos. And there's a lot of details about how that's figured out, but I will move on just to give you a flavor for the other experiments. But this was, to give you an idea of how frugally this was done. The Russians have been working on this. When I went, they had been working on it for 20 years, and they had done all of that work with $20 million, which in today's, like if you think of neutrino experiments today, even a 2 or 3 year of effort will cost a quarter of, $250 million, $300 million, which I'll show you another one where those are the numbers. So, and then I, came back after this experiment, ended up writing a proposal, convinced a publisher that this is something worth writing and publishing. So once I had that, then I started doing the other travels. And I still think that if a publisher had said no, or rather if no publisher had said yes, then I would still have done these travels. They would have just taken 10 years or longer. But as it happened, I had to then start doing them within 2 or 3 years. So because now there was a deadline. And the next, I made a series of trips to see the Large Hadron Collider. Oops, what did I do? So, and when you're writing a book which involves extreme travel, going to Geneva from London is the last thing you should be doing. you go to Geneva, and if the bus timetable says the bus is going to come at 1921, it comes at 1921. There is no drama. There is nothing for a writer to worry about. It was really bad in that sense. All of the drama was happening 100 meters underground. So this chapter was written in the form of a travel through the tunnels of the LHC. So it was not a travel above land, with any kind of mystery or danger. Everything was inside underground. So I got to see the LHC about 3 times before it was functioning. So you actually go and I stood in exactly this location. This is not a picture I took. This is one of their stock pictures. But this is the kind of scene, like you could stand there and look at this giant thing. And I won't focus on the LHC because it's been in the news so much, and in popular imagination it hardly counts as extreme anymore. So the other experiment that I visited soon after that was to a dark matter detector. Now, dark matter is, like I said, these are hypothesized particles that we think exist because we can see the gravitational influence of dark matter on normal matter, right? So, and there are theories which kind of tell us what kinds of particles these might be, and there are lots and lots of experiments. They've been going on for decades now that have been trying to look for dark matter through what are called direct detection techniques. They're essentially looking for the direct impact of a dark matter particle on some detector material. For instance, the experiment that I was visiting, which actually started in Berkeley and Stanford, the first version of it, it's called the cryogenic dark matter search. And this is essentially looking for the impact of a dark matter particle on an ultra pure crystal of germanium or silicon. And the idea would be that if the dark matter particle hits the germanium atom or germanium or silicon atom, it would basically set the crystal lattice vibrating, raise the temperature of that crystal by millikelvin, or send vibrations that can be detected by superconducting fins on the surface. All that is great in theory, but the temperature rise is in millikelvin. And if you try to put that crystal lattice out on the surface of the Earth here, there are other sources of noise that will completely swamp that signal. For instance, cosmic rays, or even our radioactivity. Even if you had shielded it from all other particles except radioactivity, and you went and stood near it, your body's radioactivity would trigger signals in that. So these detectors have to be shielded from all possible sources of noise. And one of the obvious places to put these detectors is deep inside mines, which have been either abandoned by miners or which are still functioning mines, but are available to put some small physics experiment inside. And again, I was talking to a researcher who said, I was telling him about this plan of going to extreme places, and he said, well, Minnesota is not extreme, but if you really want some drama, go in winter. So I went to Minnesota in winter. There. And as it happened, there was a storm heading towards Minnesota, and I spent 4 hours basically outdriving the storm towards northern Minnesota. So that was a little bit of drama, but that's about it. And then again, everything happened as a travel piece, going down into a mine and coming out. So this was the mine head, the equipment at the very head of the mine, and you see that cage. Just pay attention to the dimensions of the cage. That's the cage that takes you down half a mile underground. This would have been used by the miners. The mine itself was functioning from 1880s to 1960s before it was abandoned. And the miners left behind all the equipment, and the physicists took over. But that's the cage. About 6-7 people can fit into that. It's about 4 feet by 4 feet by about 10 feet. And it takes about 3 minutes to go into the bowels of this mine. And when you come to the very bottom, the door opens and you see this sign, level number 27, 2,341 feet below the surface. And if you were to turn left at this point, you will see a long tunnel. It's called a drift tunnel. This is the tunnel that the miners would have used to bring the ore out from inside the mountain. And you go all the way in. And when we went there, our guide, he basically switched off all the lights and held up a candle to kind of show you that this is the light with which the miners would have worked when they were working in the 1880s, early 1900s. They had literally this kind of light and using sledgehammers and drill bits, and maybe towards the end of their mining, pneumatic drills, but they took out something like 17 million tons of ore from this mountain. It was the biggest iron ore mine in Minnesota at the time. If you now come back to the shaft, and when the door is opened, we went left and we went into these caverns left behind by miners. If you turn right at this point, you see this. This is the new physics laboratory. Well, it's not new anymore. It's been functioning for a long time. I went there in 2007, and it had been functioning well before that. So this is what physicists have excavated. So two large caverns, about 40 feet high, 50 feet wide, and 270 feet deep. And every piece of equipment here, including that giant thing that you see there, that's a neutrino detector, which is detecting neutrino beams that are being sent from Fermilab in Chicago through the Earth all the way to this underground mine. That equipment is about 7,000 tons of steel and electronics. And everything, every little piece of this came down that cage, that 4 by 4 by 10 cage, including the excavator, which had to be disassembled and assembled underground, and then start excavating and take out all this material, and then bring in all this, equipment. So there are two such caverns, massive ones. I was there to look at these dark matter detectors. So dark matter detectors, I didn't get to see them because it was completely shielded, but they're essentially crystals the size of a hockey puck. About, I think, 6 of them go into each of these copper canisters, and there are 30 of them in total, the detectors. They're all in a cryostat. The whole thing is cooled down to 40 millikelvin and then shielded with polyethylene and lead, and new lead and old lead, because new lead is radioactive, so they need old lead to shield against the new lead. I mean, it goes on and on and on until they think that they have a detector that literally detects nothing. Or either it's being shielded from all the sources of noise, or they have managed to figure out if there is a signal, then they can explain what the signal is, what is causing that signal. So once they have that set up, then if you see an anomalous event which has the right signature for the expected dark matter particle, then they can claim discovery. So far, nothing. Literally nothing, right? I mean, this is not the only experiment happening in underground mines. There are tens of them all over the world. And I think today there was a news about another experiment coming up, null. So there's something about dark matter that really is very mysterious. We still haven't figured out what these particles are, if they are particles, if there is dark matter. I mean, there is a lot of ifs and buts going on here. But this was, for the purposes of the book, fabulous, because you could talk about dark matter. There's a whole narrative about how difficult it is to do this experiment. From there, I went to Mauna Kea. So Mauna Kea is another place which is like the Andes. It's, again, pockmarked with telescopes there, and that's where another massive telescope is being built. So in terms of naming conventions, there's this other set of telescopes where they're just naming it by the size. So the big one that's being built now is just being called the 30-meter telescope. So evocative names are not part of the astronomer's lexicon, which is amazing given what they're observing and what they're seeing. Their telescopes are named so prosaically. But anyway, I was there to see the Keck telescopes. And here you can see the inversion layer of the clouds, right? The clouds are actually below the summit. This is also the same climatic sort of phenomenon that makes the sky above clear for telescopes is also happening in Hawaii around Mauna Kea. These are the two Keck telescopes. These were the first telescopes that were 10-meter class that broke the kind of paradigm of building mirrors from a single block of glass. So by the time you got to anything beyond 8.2 meters, it became extremely unwieldy to have a single piece of glass for the telescope mirror. So they came up with a method where you segmented the entire mirror. So each Keck mirror, which is 10 meters in diameter, is made up of, I think, 36 segments. So each segment is 1.8 meters. And when you think about it, 1.8 meters is itself already a huge telescope, and you put 36 of them together. And then these segments have to be very, very precisely aligned, because as the telescope is moving, even the smallest kind of change in the curvature can mess up your signaling or your data collection. So again, there are actuators sensing how these things are moving relative to each other and constantly pushing and pulling. So in the case of the VLT, the 8-meter class mirror, had 150 actuators that was controlling the curvature of the entire mirror. Here, there are 3 actuators per segment, and each segment is being individually controlled, so the overall curvature is exactly what you want as the telescope is tracking some object. And again, this was an amazing piece of engineering. Also, I think they're still, until the big telescopes come, they're still the largest telescopes around. from there, it was a trip to see. In this case, the telescope was actually not yet constructed. I wanted to write a chapter on radio telescopes, and as it happened, the square kilometer array was being planned. And when I went, there were two lands on this planet that had been chosen as the possible location for this future telescope. The square kilometer array refers to a radio telescope which will have about 3,000 antennas, and the total collecting area of the 3,000 antennas will be 1 square kilometer. And it's almost impossible to visualize sort of the size of this thing. And at the time, South Africa and Western Australia were in the running, and I chose to go to South Africa. I could have just as well gone to Western Australia and written the same story. So I was, here again was a writer's choice. I wanted something different than the rest of the places I was visiting. So in terms of the science, it could have just as well been Western Australia, because I was still writing about a possible future telescope. The telescope was not different, but the land was. The history of the land, the politics, all of that was different. So from a writer's perspective, it was a very deliberate choice to go to South Africa rather than to Western Australia. This was the land I saw. It's called the Kuru. It is just south of the Kalahari Desert, arid land. So when I went there, this is all. It was just empty land, and this was the land where this is the place where the heart of the square kilometer array is going to be situated. So this was in 2007, and when in 2012 the International Radio Astronomy community decided to award the telescope to the people who were going to construct it, and they decided to split the telescope. And with radio telescopes, you can do this. So they gave the high frequency part to South Africa and the low frequency part to Western Australia. So this is the region where the high frequency part of the radio telescope will be sited. So 3,000 antennas, about 2,000 of which will be in a cluster. So those 2,000 which are going to be in a cluster will give the telescope its sensitivity, and then there will be antennas spread across Africa, possibly spanning 3,000 kilometers, and that span is going to give the telescope its resolution, because they can then do very long baseline interferometry. And the low frequency component, so the high frequency will be looking for radio waves from about 1 gigahertz up to 20, maybe even 30 gigahertz eventually. And then the low frequency component is signals from the cosmos which are below 1 gigahertz, going all the way down to maybe 100 or 70 megahertz. And that's done not using these. And so when we think of radio telescopes, we kind of think of these dishes moving around in concert, like the Very Large Array in New Mexico that you might have seen the movie Contact, and those were radio telescopes. But actually some of the more profound work in radio astronomy has happened because of things called phased arrays, which are literally just television antennas stuck in the ground in arrays, and then you use electronics to figure out how to focus the antenna or the telescope in the sky. So that part is being built in Western Australia. And from South Africa, the next part was possibly to the most amazing place where astronomy and cosmology is being done, which is Antarctica. I was there to witness something called long duration balloon flights, and this was my first sighting of Antarctica from the plane. The journey to get to Antarctica itself was quite, not hard, but long. I was in London at the time, so London to Los Angeles, Los Angeles to Auckland, Auckland to Christchurch. 2 days of being in Christchurch while the US Antarctic program kits you out with extreme weather gear. So I remember asking them, what should I bring for clothing? And they said, please don't bring anything. You will not know, you won't have a clue as to what to bring. Just come and we'll kit you out. And you really have to, they give you about 30 pounds of gear that you have to then wear as you get onto the plane, because you don't want to land somewhere where the gear is not on you. The frightening part is you're basically flying over the ocean. So if the plane crashed, you're wearing 20 pounds of stuff that you can't get out of, and it's pretty much a guaranteed watery grave. I don't see the point of that. But anyway, they had their reasons. We could not get onto the plane without wearing all that stuff, including very heavy boots and all sorts of stuff. And this was a US military transport plane, C-17, which is this massive plane meant for transporting cargo. And as passengers, we are sitting on the sides, and there are just 2 portholes for windows in the entire plane. And looking out, this was the first sign, the blue waters of outside Antarctica, the Southern Ocean with the glaciers, the icebergs. I was there to watch the launch of instruments like that. These are basically particle physics experiments that are being flown to the edge of the upper stratosphere. So experiments that weigh almost 2 tons, that are taken up by balloons to about 40 kilometers into the upper stratosphere. And the reason for doing these oh, by the way, that's Mount Erebus. I think that's, if I'm not mistaken, that's 12,500 feet high. It's the southernmost active volcano. It's quite amazing. You are in Antarctica, everything is frozen. There's ice, there's literally a glacier on the very top, but it's an active volcano. So that's how cold it is, and that's how crazy that place is. So these experiments, the reason why they're doing it in Antarctica is because every austral summer, in the summer in the southern hemisphere, there's something called a circumpolar anticyclone that sets up in the upper atmosphere. So there's basically a air stream that's going counterclockwise in the upper stratosphere. And the idea is to get a balloon up into that airstream, and then it's just going to keep going round and round over your head. So if you try to launch such a balloon on the continent somewhere, it will just go across the continent, and then you have to run after it, and you don't know where it'll come down. Here, you can just watch it going around a couple of times, and then hopefully bring down the payload using parachutes pretty much where you want it to come down. It doesn't work like that at all. The stories about recovering payloads are harrowing, but nonetheless, that's the reason for doing it there. And by and large, they succeed, but they still have pretty dangerous missions to get the payload back. So I was there to watch one of these, and just to give you a sense of what it takes to launch the balloon, to give you a bit of historical context, in 1904 or 3, I'm hazy with these numbers now. These things used to be at my fingertips at one point, but it's been 10 years. But I think in 1903 or 1904, Robert Falcon Scott was the first person to rise up in a balloon over Antarctica. His balloon had a volume of about 8,000 cubic feet. It was filled with hydrogen, and it was tethered to the ground. So there was a basket in which Scott could get in, or any one person could get in, and the balloon would rise, and the whole thing rose up to a height of 800 feet, right? So 8,000 cubic feet of hydrogen rose to an altitude of 800 feet. This balloon, from the tip of the payload to the top of the balloon, is 1,000 feet, just the balloon, right? So, and what's happening here is the payload is on a launch truck. It is connected to a parachute. It's somewhere here are the explosives, and then the balloon fabric is being filled up with helium. So, and you see these are helium fill lines. So there are two massive, and again, all of this stuff is being taken via ship or plane, mainly by ship. Even the tankers with helium. There's a truck somewhere outside here which has helium tanks. As we walk past, so imagine supersized versions of that on the ice. So we're standing on the Ross Ice Shelf here. The Ross Ice Shelf is the largest ice shelf on the planet. It's about 200 feet thick, and for some reason, it's always referred to as being the size of France. I have no idea what that means, but if you know what the size of France is, the Ross Ice Shelf is the size of France. If you're from England, you call it the size of Wales. I think here it's the size of Texas. Doesn't matter. I have no idea. But it's huge. And it was interesting that when I started doing the first few trips, I had a very, very bad camera. It was just a point and shoot. And I realized very soon that I needed to learn photography and get a better camera. So by the time I got to Antarctica, I had started figuring out how to take better pictures. So I really like this picture. But this is helium filling, the balloon being filled up with helium. I have a video to show you now of the launch itself.
Okay, release the balloon, release the balloon, release the balloon.
It's a different payload. And to give you a sense, so that payload, I don't know if this one was 2 tons, but in general these payloads are 2 tons. The balloon fabric is 0.0008 inches thick, like a sandwich wrap, right? And despite that, it is so big that just the fabric alone weighs something like 5,500 pounds, or almost 2 tons. And then 2 tons of payload, and then all the helium that has to be put in. There's about 37 million cubic feet of helium going into that balloon, which the balloon doesn't inflate fully because of the temperature at sea level in Antarctica. But by the time the balloon reaches cruising altitude at 120,000 feet, it is 400 feet across. It is so big, it's the size of half a full moon, and you can stand at sea level at McMurdo and look up and you can see the balloon. It's that big, right? And then it goes around for 2 weeks, maybe 3, and then the payload is brought down. So you detonate the explosive, and the payload detaches and free falls for a while. The parachute opens up, and then hopefully it falls where you can recover it. By and large, they've always recovered it. And the experiments that I was looking at were looking for, at least the way I was framing the story for my book was, the experiment was looking for signs of primordial antimatter. There's a huge question about why there's only matter in the universe and no antimatter, because our theory is if the symmetries of physics have to be are correct, then matter and antimatter should have been produced in equal amounts. Obviously, that's not happened. So this was one way in which, if you could detect primordial antimatter, an anti-helium coming from somewhere in deep space, that's a very clear sign that there are galaxies and stars that are made of antimatter as opposed to matter. I mean, the term antimatter matter is just terminology, but something with the opposite charge. So from Antarctica then, or rather from McMurdo, which is on the coast, I got to go to see the IceCube neutrino telescope at the South Pole. So it's a 3-hour flight from McMurdo to the South Pole in a Hercules LC-130. This is a plane on skis. This is both the arrival lounge and the departure lounge at the South Pole. You get off the plane and people are ready to get back into the plane, because the engines are not shut off. You stop the engines for any length of time, and that's it. The plane doesn't get off the ground. The skis on which it has landed will freeze. The engines will freeze. It'll take a whole lot of energy to basically thaw the thing. So the best way out for them is to keep the engines running for half an hour. Everybody gets out. The people who have to get back to McMurdo get back in. The cargo is unloaded, reloaded, whatever, and then they get off in 30 minutes. Any longer than that, then they're wasting fuel. So this is landing at the South Pole. I was there to see the building of the construction of this thing called the IceCube neutrino telescope. So the Lake Baikal neutrino telescope that I showed you earlier, were these photo detectors that had been submerged into the water. Right? The idea is the same. You're still looking for the smashing of a neutrino against a water molecule. Here the water molecule happens to be frozen, it's ice, but the essence of the argument is the same. You're instrumenting 1 cubic kilometer of ice in order to see the Cherenkov radiation that is emitted when neutrinos smash into water molecules. But how do you instrument 1 cubic kilometer of ice? And these people came up, and rightfully, or most of the people are from Wisconsin, so ice was a non-issue for them. But again, you have to drill 2.5 kilometers into the ice. The ice sheet at the South Pole is about 3 kilometers thick, right? And you have to drill, and the first 1.5 kilometers of the ice is pretty cloudy because of dust that has settled over tens of thousands of years. You really need to get deep into the ice sheet before the ice becomes crystal clear. And so they literally had to use boiling hot water at 1,000 psi. They're pumping hot water into the ice, melting a hole about 0.5 meter wide, and the drill, which is essentially a hose that is spewing out hot water, is melting the ice, and the drill is weighted down with 0.5 ton of steel. So the whole thing, as the ice is melting, this thing is falling down like a plumb bob, and it goes down 2.5 kilometers, and it's so precise that at the end, that hole has deviated from the vertical over 2.5 kilometers by just 1 meter or less than a meter, right? And then it takes 24 hours for this hole to be drilled. So they're boiling water here in their and then they're pumping that water into the ice, melting a hole 0.5 meter wide, 2.5 kilometers deep. It takes 24 hours to do that. It takes 10 hours for the drill equipment to be extricated from the hole, and now you have a hole that's full of water. But you have just one day to sort of put your instruments in, because if you wait any longer, the hole freezes shut, right? So you just have another day to lower down these detectors, and so that's the expanse at the South Pole. So this is what they're doing. There's basically a Kevlar cable, 2.5 kilometer long Kevlar cable that is being fed into the hole, and every so often they're connecting this thing called a digital optical module, which is essentially a photomultiplier tube with, it's a computer in its own right, each one of them. And they drilled 80 holes into the ice, and into each hole went in 60 of these digital optical modules. So there are 4,800 of these artificial eyes that have been used to instrument 1 cubic kilometer of East Antarctic ice, which is well below the surface of the ice sheet. And when I went, they were still building it. I think they had finished about 59 or 60 of these holes. This got completed a few years later, and they have been phenomenal in terms of detecting neutrinos from outer space. So, atmospheric neutrinos are now just a non-issue. You detect them willy-nilly now. So the real treasure is astrophysical sources that are spewing out very high energy neutrinos, and they've managed to detect those things. This is the hole. That's the thing that's the optical module going into the hole that had been drilled. And one of the things that I was told was, don't turn your back on the hole. And I, of course, had no intention of doing so, but just even leaning into that. The drillers would sit in the South Pole station and joke about how easy it would be to murder somebody at the South Pole, because all you have to do is push them into one of these holes. That's it, they're gone, right? And then you have to change the flight manifest so that you can make sure that the flight manifest shows that they have somehow flown all the way to Christchurch. That's it, right? And the flight manifest can be, I presume, easily manipulated out there. Who knows? I shouldn't be saying these things. Can you edit it out when you're... so anyway, it's an amazing place. So then one of the things I wanted to do in this book, well, let me first talk about the Mount Wilson Observatory. This is, I wanted to do some history. This is where observational cosmology began. Mount Wilson is right next to Pasadena, and that is the 100-inch telescope that Edwin Hubble used to figure out that our universe is not just the Milky Way, that there are extragalactic nebulae. He always used to call them extragalactic nebulae. He never called them galaxies, but that's what they are. They're galaxies beyond the Milky Way. So he figured out not only that the universe was more than the Milky Way, but that these galaxies are receding from us in with a very linear relationship called the Hubble distance velocity relationship. And it was our first indication that if you work backward in time, all of these things would have been in one place. It was the first indication of observational indication that the universe had begun in a Big Bang. And then that's when, so one can say that this is where observational cosmology began. This was built by George Hale, the astronomer George Ellery Hale, in the early 1900s, and now it's still functional, but things have changed around LA in terms of light pollution, but it's not really the telescope that it used to be. So one of the things I wanted to do in this book was, as a metaphor, I wanted to visit a couple of monasteries. So not really conflate the two. I didn't want to make any connections per se between what monks are doing and what astronomers are doing. I just wanted to make a metaphorical connection to give people a sense of what the astronomers are doing by talking about what the monks are doing. So I thought, let me visit a couple of monasteries. And as it happened, there's a Camaldoli's monastery just further north from Pasadena. If you just drive up Highway 1 along, somewhere near Big Sur, there's this monastery where you go and you're completely silent. And so I was trying to write about being in such a place to give a sense for what Mount Wilson might have been way back in the early 1900s. And you can't talk to anyone there except at the reception where there's a monk, and you can go and talk to the monk for whatever reason you might need to. And here I was trying to figure out how to find some connections between what I had just visited, which was Mount Wilson, and monks. And I was telling this monk about my journey so far, about having just come from Mount Wilson, and he started smiling. He says, George Hale built the observatory there. I said, yeah, I know that. And then he said, my name is Father Robert Hale. It turns out that Father Robert Hale and George Hale are descended from the same guys, Thomas Hale, who left England in the 1600s, came to America. So here I was trying to find metaphorical connections, and there was an actual lineage connecting one monk to an astronomer. So for a writer, this is gold, right? You don't have to work at all. You just have to describe what you're observing, and your task is done. Let the readers make up their minds whether there are connections, but you just describe what you're encountering, and it was fabulous. So this is just a scene of a woodpecker outside my silent dorm window. The last journey was to a place called Hanle in Ladakh in the Himalayas. So this is a place in the Himalayas beyond the 8,000 meter peaks. So this is the telescope. The telescope itself is rather rudimentary at this stage. Again, in terms of seeking a metaphor, it was really all I had to do was describe what I was seeing, because I was describing a telescope, and right across is a 400-year-old Buddhist monastery, right? So again, no effort at actually trying to make any obvious connections. You're just describing as a person that's observing something, and the writing does its job of creating connections in readers' minds if they're predisposed to it. If not, it's an innocuous comment, right? So it's actually worked out really nicely. So let me now, how are we doing for time? So I'll try to quickly run you through some of those were the sets of travels that I did. Now the act of putting together the book started. So I was writing as I was traveling, but these are all disparate chapters. Now I had to figure out what was the overarching theme that the book was going to be dealing with. And the obvious thing at that time was that, and even it's true even now, it's just that the numbers have changed, but we think that about 3/4 of the universe is made of something called dark energy, which is the energy of the vacuum of space-time itself. This is supposed to be the thing that's causing the acceleration of the expansion of the universe to accelerate in recent times. Quarter of it is supposed to be dark matter, which we can detect its gravitational influence on normal matter, but we don't know what it is. And then, the rest of physics, particle physics that we have, describes normal matter, which is about 4%. Again, these numbers have changed since I wrote the book. So basically, I had to identify the big questions that the book would answer. So the nature of dark matter, the nature of dark energy, the origin of mass. Remember, this was before the discovery of the Higgs boson. So the book could actually take on this question of the quest to find the Higgs, which is basically the story of the origin of mass. The question of the matter-antimatter asymmetry, which is still unresolved. Questions about, are there other universes out there? This leads you into discussions about string theory, about other ways where multiverses pop up into the discussion in physics. Again, I was pretty agnostic about taking a position on this. These were just ways in which you could bring in current thinking about what's happening in cosmology. And then the big question for physics today is reconciling general relativity with quantum mechanics. So how could these experiments shed light on this unification? So these were the big questions that I set it up in the beginning of the book. And then you had to kind of start thinking about how to place all the chapters, because science books, most popular science books, have one thing going for them, that is they have a very self-evident narrative, which is just the accumulation of knowledge. There is something about writing a science book that has a linear timeline that works really well, because you can just use the progression of knowledge as a way to drive the narrative forward, right? So the mysteries are mounting, solutions come about, new mysteries happen, and you go on, and that works really well, and it's pretty much the standard way of writing a science narrative. But this was complicated because except for the first chapter, which was historical, every other chapter is about physics that is happening right now. Every other chapter, the physics was just as current, like the physics in chapter 2, the particle physics was just as sort of developed in terms of complexity as the physics required for chapter 9 about the Large Hadron Collider. So this was a challenge, having to just introduce the right amount of physics at in each chapter, so that the complexity is building up over time, but yet when you need some physics to explain, say, the dark matter experiment in chapter 2, you still are able to do it. So that was a problem. And so a lot of effort went into trying to structure the book, where the structure was not obvious. Each chapter had its own narrative structure, which was the travel. That was easy. The larger narrative of how the science is flowing through the course of the book was the harder part. And of course, I could not present the travel in the same sequence as I did the travels, because that also had to be juggled. And you have to do it seamlessly, where you're not lying, but you also don't want to say something that's obviously false. So it's all in ambiguity. So as you write. And then, the book, I remember in the first couple of drafts, I even I, as a writer, was getting claustrophobic reading my own work because there was too much dark energy, dark matter, every chapter was about that. So somehow I had to find ways of getting out of that, and that worked in the third draft. I could figure out a way of breathing again. Then, of course, structuring the individual chapters, there was a big question of how do you get all the theory into this. So in the first draft, I did this rather kind of easy thing, which is write 9 chapters based on my travel, and then wrote a final chapter about all the theory, lumped all the theory in the very end and said, okay, done. I sent the draft to my editor, and she liked all of the 9 chapters, and the last chapter, she just put one big red mark around it and saying, what have you done? I mean, how can you put all this stuff at the very end as if the reader would want to read this now? So she basically said, look, take that out. Take the entire chapter out and figure out a way to move all that theory into the first 9 chapters. So as it happened, as I started doing it, I realized I needed one more chapter, which could not be a travel chapter because it was about satellite missions. So I wrote about Planck, which is a cosmic microwave background detector, and used that for tying up some loose ends about the theory. But much of the theory that I had just put into one chapter had to be dismantled and sprinkled throughout the earlier chapters. And then as a writer, you're also thinking all the time about how to take the reader from paragraph to paragraph, from section to section, from chapter to chapter. And a lot of this effort is about crafting transitions. So the last paragraph of a section connects somehow to the first paragraph of the next section. The last paragraph of a chapter somehow connects to the first paragraph of the next chapter. Things like that. You have to think about all these things. So I just want to give you a sense of what it takes. So for instance, in the first chapter, which is about the Mount Wilson Observatory, it starts by describing Hubble's work, all of that, sets up the history. And then now I have to transition to talking about the monastery. Why would you suddenly start speaking about a monastery, right? So you have to give a rationale to the reader. The reader should be convinced that this belongs in the chapter. So this was the transition paragraph, right? So this is what I wrote. The greater Los Angeles area, which Mount Wilson overlooks, is hardly the quiet, unpopulated, unpolluted region that Hale once found so appealing. However, there is a section of California's coastline that still remains pristine, providing a glimpse of what Hale might have encountered. These are the forested slopes of the rugged Santa Lucia Mountains, about halfway between Pasadena and San Francisco. Amid these slopes is a Camaldoli's monastery where solitude and silence are a way of life, much as Hale desired for his astronomers. So this is a transitional paragraph where you have elements of something that has happened before, elements of what's going to come, and now you're telling the reader that, okay, we're now going to talk about something else, but you're transitioning through this, right? Also, you have to think about chapter openings and chapter endings. So this is a scene from the Kuru, the South African land where I went to see where the telescope might be built. And this was the opening paragraph, right? You're just setting up a mood. Just south of the Kalahari Desert is a region of South Africa where no physical feature proclaims its past too grandly. You have to be a geologist to look beyond the unrelenting barrenness. This is a land so arid that sheep farmers need hectares of grazing land for a single animal. The Khoisan people of southern Africa call it the Kuru, the land of thirst. A few 100 million years ago, it was anything but. The shards of shale underfoot speak to a time when this land was at the heart of the supercontinent Gondwana, much of which was covered by a vast ice sheet. And then it progresses to describing the land and why it's such a great piece of land for building the radio telescope and so on, right? And this reference to the ice sheet was important because I'll now show you the paragraph that this chapter ends. The whole chapter spends time talking about radio astronomy and the land where it's going to be built. And then it ends with a reference to the next chapter, right? The Kuru promises to be a significant part of cosmology's evolving story, but there is another land far bigger than the Kuru that is already writing its own narrative. About 50 million years after Africa split off and drifted northward from Gondwana, another bit drifted south and ended up at the bottom of the world. A land more pristine than the Kuru, Antarctica is fast becoming our most sought-after window on the cosmos. Though it remains as dangerous for the untrained traveler as when humans first started exploring it a century ago, it was with great anticipation that I set off for the frozen continent, cosmology's biggest and boldest bet yet. So this is a transition. You're basically telling the reader that hopefully you've interested the reader enough to turn the page. That's all you want them to do. And this is Antarctica. This was one of the first things I saw out there. This is a glacier that has descended from Mount Erebus. And this is the Ross Ice Shelf in the foreground, and that's a section of a glacier that you're seeing. Antarctica was really hard to write about. I struggled for a long time about how to open the chapter because there's nothing in my immediate experience that was allowing me to connect with my readers. And most readers also will not have any way of connecting with what Antarctica might be. As it happened, I found somebody else. As writers, you're always looking for things that others have said, which might help you in how you write. And I did find something that was perfect. It basically was making the point that Antarctica is impossible to write about, but done very poetically. So I just took that. Right? This is the opening paragraph of the chapter on Antarctica. Before I set out for Antarctica, I kept hearing expressions like, see you on the ice. And so how long will you be on the ice? The ice, I realized, was an insider's term, a tacit acknowledgement of our inability to describe Antarctica in anything but the most mundane language. Francis Spufford claims in the introduction to his anthology of writings about the frozen frontier, nowhere else on earth is it so clear that a place has an integrity apart from what we might say about it. Nowhere are words so obviously ineffectual a response to what just massively exists, whole and complete, and in no real need of translation. That allowed me to then start saying something about it. But it was a way of getting away from this problem of not knowing how to say something about it. Right? Again, I think we're running out of time, so I'm going to skip this. The other thing that happens as a reporter, somebody was asking me whether I was a journalist or a science writer. I'm really a journalist. So I'm reporting, listening to what others are saying. And sometimes our sources say the most amazing things. And this is how the chapter on Antarctica ends. In the words of a glaciologist who has spent way more time than I'll ever get to spend on Antarctica. He said, NASA glaciologist Robert Binstrander spoke of the absolute stillness he felt in Antarctica, the absence of anything familiar. You are there in the middle of nature, and nature is expressed in very simple, impressive, and intensive terms. You can't ignore the temperature because it is cold. When the wind blows, you can't ignore the wind because it dominates your awareness. And the surface that you're standing on and walking across and living on, that's all there is. It's omnipresent and it's overwhelming. There is no other distraction. I feel I can't avoid the issue of our place in nature and our uniqueness and smallness. And sometimes there are people, this is verbatim, this is how we spoke. So, it's, again, for a writer, it's absolutely phenomenal to find things like that. I will skip this and just show you. So this is the ending. So this was the monastery from the telescope up in the Himalayas. So this is Hanle. That's the Buddhist monastery. And my last, I had to end the whole thing with a point I wanted to make. Throughout the book, there is this reinforcing of the idea of stillness. And I mean that in many different ways throughout the book. And it's of particular relevance to physics experiments. There needs to be a certain kind of quietness, whether it's quietness from radio noise, for optical pollution, all sorts. So essentially, everything that is happening in extreme physics requires bringing the noise boundary down, right? So there is this overarching theme of silence and stillness, and then the monasteries and the talk about the monks are kind of reinforcing that metaphorically. And I wanted to end with that, the whole book with that message, right? So this is how it ends. I became aware of the deep silence enveloping me. The monk. So I'm standing right now on the telescope, 14,000 feet up in the Himalayas, looking at the monastery, and that's the last paragraph. I became aware of the deep silence enveloping me. The monks had built their monastery here for a reason. Now the astronomers were taking advantage of the intense quiet to find answers to profound questions. It was abundantly clear standing in Hanle, as it had been in places like the South Pole, Lake Baikal, Paranal, and the Kuru, that the natural calm of these places is what makes them ideal for cosmology. We need to protect them just as we protect our inner peace as individuals. If we pollute them, we will destroy our best chance of deciphering our own beginnings of understanding ourselves. I will end with that. So that's the book. Thank you very much.
Time for a few questions.
Yeah.
I'm curious about two things. First, how did the funding for this travel work? Did the publisher...
So, no, publishers unfortunately don't give you money for travel. I wish they did. So the way it worked, the first two trips I did on my own money. I had to. There was no way out. So the Chile and the Siberia trips came out of my pocket. I mean, everything came out of my pocket. But what happened was, once I wrote the proposal and got a publisher interested, they just give you an advance to write a book. They're not concerned whether you spend it on food or whether you spend it on travel. It's just so I had some advance. So I started using the advance for the rest of the traveling. And the only place where I had funding, which could not have been done without the funding, was the trip to Antarctica. So there is a program called Artists and Writers in Antarctica, which is run by the NSF. you can apply. And if you're selected, then you're in really good hands, because they will then basically take care of your entire trip. So I was taken from London all the way to the South Pole and back, and on the U.S. Antarctic program took care of that. So that would be a major part of the funding for that trip. But the rest of it was from the advance and from my own pocket.
Okay.
Yeah. One more question?
Second question is, I imagine you must have had like hundreds of pages of notes about your travels. So how did you organize these, and like did you use Google Docs, or like what tools?
So say the last thing again.
What tools were you using, like Google Docs?
I'm pretty primitive. I just open a folder first in my desktop saying, Edge of Reason or whatever that working title was, and then subfolders, and just start dumping files with the intention of looking at them later. And half the time I never look at them. It's just that you're reading so much as you're going along. There are hundreds and hundreds of files. Not just that, the transcription of my interviews. If I had just printed out what I had transcribed, there would be stacks of paper that high, right? And you have to turn that into a book 300 pages long. I'm not organized in any sophisticated sense. It's just literally just folders in my computer where I'm putting in stuff, and I'm hoping that I know where to look. It works out, but there are other ways in which you can do this. There are much better techniques out there to organize your material. I thought I would improve with the next books. I haven't. Even the last book I did exactly the same thing, so something wrong with me there. Yeah.
I imagine one of the struggles in writing these books is trying to figure out how in-depth you can go into the physics of it without,
So for me, there were two things, right? I wanted to hopefully not leave any reader behind. That's always a task that you have. But I also did not want to shortchange the physics, right? The science. So it's a balancing act. There are times when you have to, walk a very fine line. But I really never wanted to write about the science in a way that feels like you're talking down to your reader. You cannot do that. I mean, you should not do that. You can do that, but you should not do that. It's a challenge. And that's something that you learn. It comes with practice.
So, it seems like lots of books are written about physics, or popular books, and it's very easy to get to readers with just being familiar with nature in some sense of the word, also being familiar with this amazing technology that you talk about, that is, and maybe the dangers of getting it. How would you write a similar story about intellectual discoveries, like things happening in a Berkeley cafe, like the fact that you can use hard problems to do cryptography and electronic commerce? Or how do you do a particular algorithm that like FFT that
it would be a different kind of book.
I know, but what access do you imagine into the imagination and motivation of a reader to get their attention? Maybe we need the Simons Institute in Antarctica, but
I mean, there's always this attempt to try and connect it to. So, if you're talking of cryptography, there's obvious connections to what's happening, with the internet, but that's a very small part of the storytelling. I don't think that really is the reason why people. So, there are books where people will read it because of its intellectual content. So if it can be still written in a way where the intellectual arguments are driving the narrative. So it will be in the art of writing it. You're right that there are no obvious ways in which you can connect it to people's lives, or create this kind of grandeur with talking about the South Pole. But I think there are books where there are books about, for instance, the debate over the nature of free will. That's a purely intellectual argument, but it appeals to people. So there are people, there are books that can be about purely intellectual arguments. They are more difficult to write. And I, as a writer, would also look for the motivations of the researchers. The researchers themselves can become part of the story more than maybe they are in my, this narration. Here it's the instruments and the people building the instruments, but, it's not totally obvious, but how, what answer to give you at this point without knowing the background of the researchers who are doing it, the background of the field itself. But there are books that have been done like that. So
I know. I was just pointing out that intellectual endeavors that happen in
Yeah.
the mind of a person
Yeah.
are much.
They're fascinating, and there are books that work beautifully when only focusing on that too. Yeah. Oh, hi.
So out of your readers, how many you think had background in science? I mean, whom were you targeting?
The idea was to target anyone who would be interested in, following along on this journey.
So you have to have some familiarity with science to.
High school, I would imagine, a little bit.
So you can make it accessible to someone with just high school physics?
Yeah, I mean, there are things there in the book where you always have to write it in a way where if the person is unable to grasp the full import of what's being said, it's at least written in a way where they can get the gist of it and still move on and not feel like, oh, I can't go on any further, right? So a lot of it is the trick of how you write these complicated pieces.
The list of big questions you gave, I wonder how any high school student would relate to any of them.
Oh, so that was just a list for telling you about what the book is about. That's not how it's written. So if you read,
okay.
No. I don't just start with a list of big questions in the book, right? The book literally starts with me sitting with Saul Perlmutter in a Berkeley cafe. It's a people story. I'm just talking to him, and the story is emerging. So
you convey the import of those big questions to the high school.
through the writing, through the writing. There's so many historical things you can, like even the act of even the discovery of dark matter itself is just a story. It's about people pointing telescopes and calculating velocities, and so you just keep building up the arguments, and suddenly you are at dark matter, and you haven't realized that you arrived at that conclusion. Yeah.
Okay, I think we're running out of time, so
Right,
please join me in thanking Anil again.
Thank you very much.